In the previous video, we found the derivative of the function f of x equals the square root of x. And we found the equation of the tangent line to that curve at the point 4, comma 2. And I have a question here for us to consider. What is the slope of the tangent line to the function, the same one, f of x equals radical x, at the point 0, comma 0? So if you recall from the previous video, we're not going to go through it again. You can look at that if you want. That for f of x equals radical x, we found the derivative is equal to 1 over 2 radical x. And remember that the slope of the tangent line is given to us by the derivative evaluated at a particular x value. So let's remember what the derivative is for this function, and also more generally that the slope of the tangent line is given to us by the derivative. So the derivative gives the slope of the tangent line at a point. Okay, so what we would want to do is plug in x equals 0 into the derivative. If we do that, though, we get 1 over 2 times the square root of 0, which is 1 over 0, and that is undefined. That is undefined 100% of the time. A 0 in the bottom is bad. It's not going to give you a number. It is undefined. If we look at the graph of the function y equals x squared, just given to us on the left here, what's going on at 0? So the function, if we just approach 0, the limit, the y values are heading towards 0, but it looks like that the graph is getting more and more vertical, or kind of straight up and down. So the slopes may be becoming larger. I don't know. Let's see what happens as we let x approach 0. From the right-hand side. Just because of the domain of the function, we only want to take positive x values. So in other words, let's find f prime. We're not going to do a limit or anything formal here. Let's just find f prime of, I don't know, 0.1. Okay, so we'll do 1 over 2 square root of 0.1. So that comes out to be 1.58. So in other words, if we look at the tangent line at the x value of 0.1, let's see here. That's really I don't know, maybe about here-ish. Here's an approximation of that tangent line here. So the slope is 1.58. And here's the x value of, I'll just make a dot here for the green, right, at x equals 0.1. Let's do 0.01, x equals 0.01. So let's do f of 0.01, find the slope of that tangent line. And you plug 0.01 in, you get 5. 1 over 2 radical 0.01 gives you 5. So as you are getting closer, 0.01, that's super close. I'm gonna have a hard time sketching all of these in here. 0.01 might be here. And so it's a lot steeper, right? Here the slope is equal to 5. So that's this one here. 0.001, let's see what happens when we plug that in, f of 0.001. One over 2 times the square root of 0.001. That comes out to be 15.8. So this is even steeper, 15.8. So let's see. Yeah, I'll try. Let's like somewhere. I can't even. It's too thick. But somewhere like this, right? Pretty steep. Something like that. So here the slope would be 15.8. We won't sketch it in, but let's just check one more, like 0.0001. That's really, really close to 0. When we do that, we get 50 out. So that would be a really steep line, like somewhere here on the curve. And, you know, it has a very, it's almost vertical. It's very steep. Okay, so as you are approaching x equals 0 from the right-hand side, the tangent lines become more and more vertical, and the slopes become larger. They're approaching infinity. I know 50 isn't close. It's not too large, but compared to where we started with 1.58 at just 0.1, it's pretty large in comparison. And if you want to just jam a bunch of zeros like on your calculator and just see like 0.00001, you're going to get a really large number for the slope. Okay, so the idea with this, or the point that I'm trying to get across, is that for this function right here, what this is showing us is that as x approaches 0 from the right-hand side, again, just because of the domain, the tangent lines, or the tangent slopes, approach infinity. And the tangent lines become vertical. Or the tangent lines become almost vertical. Like straight up and down, right? Vertical line. Vertical lines have undefined slope, so this makes sense, right? It's all connected with that vertical line, really, really steep slope if you're talking about a limit. So the connection, or like the word, I guess, that we use to describe this idea, when you can't find a tangent line to a point, even though there is a point on the graph, like 0, 0 is a point on this graph here, not all places have tangent lines. There are some cases where a function just doesn't have a tangent line. And that is called non-differentiable. Okay, so we say that the function here, the original function, f of x equals radical x, we say it is not differentiable at x equals 0 because we cannot have a tangent line there. There is no tangent line slope. The derivative is undefined. You can't plug a 0 in. Okay, so this non-differentiable, not differentiable at a point means that there is no tangent line there or no tangent line slope, right? You can't find a numerical value for that. So this vertical behavior, or tangent lines becoming more and more vertical, is one way that a function could have this point where it's not differentiable. There are several other ways too. So this is a term, again, called differentiable or differentiability. It's a really long word, differentiability. This means that a function has a derivative value or has a tangent line. And there are 4 main reasons that a function can fail to be differentiable at a particular x value. The first reason could be if there is a discontinuity. So that's not really what was shown in the previous example, with radical x. But if there's a discontinuity, then the function doesn't have a tangent line there. So if there's a discontinuity at the point. So remember, functions aren't continuous when they have a vertical asymptote, when they have a hole, or when they have a jump in the graph. So at all three of these places, vertical asymptotes and holes, there just aren't a function, there's no point on the function for you to put a line at. So that's why there's no derivative there or no tangent line. It's not differentiable. Jumps, same reason, except from either side, the slopes are different if there's a jump in the graph. And so how does the tangent line know which slope to take when from either side, you have a different kind of slope. So any discontinuity will be a point where the function's not differentiable. The second reason is if there is a vertical tangent line at the point. Now this is not a vertical asymptote. This is a vertical tangent line. So we kind of saw that the previous example, except it didn't, the function kind of stopped, which is, yeah, I guess we could call the previous example one of these cases. But in general, this might look like where the function is just vertical at a point. So somewhere like that. Is the function straight up and down there? Maybe that's not the greatest. Maybe that would be better. So right here, where the function is just straight up and down, that'd be a point where there's a vertical tangent line, right? To draw the tangent line here, it would be like that. So because these lines don't have slope, they have undefined slope, we will call this a point of non-differentiability. Okay, the third is if there is what we call a cusp. So these are vertical tangent lines that come in together from different sides. So something like that. This would be considered a cusp right here at this point. So it comes in vertical from both sides. I guess it's true of the vertical tangent line as well, but these are doing like one is going down from left to right and the other one's going up from left to right. Whereas in the vertical tangent line case, they're both going up from left to right or down, or their direction matches, I guess, from left to right. So you could have cusps that look like this as well. And in the previous one, you can have a vertical tangent line, of course, that looks like this, like it could go the other direction too. Something like that. And then the last case is called a sharp turn or a corner. So a cusp is sort of like a sharp turn, except it's a very specific kind of sharp turn. A sharp turn at the point would look like more of like a cornery type thing. So like this. Like this. So the slope from one side, they're not coming in vertically towards as you approach the sharp turn or the corner there. Okay, so like right here, this would be the corner. They both just have different numerical slopes. Like one is positive from left to right. This line is negative from left to right slope. And so the slopes aren't matching. They're not together, as they don't agree as you get to that corner. They could be like this as well. But they have different slopes from either side. But they're not coming in vertically. That's just the difference between a corner and a cusp. Okay, so I've got a very interesting function here. We're going to find the points at which the graph of this is not differentiable, and state why. And then also look at some limits of the derivative from this graph. So pause this, copy down the graph, and then see if you can kind of identify where this function is not differentiable. Okay, so going left to right, and keeping in mind our 4 reasons. One of them, the first one, is a discontinuity. So I see a discontinuity here. There's a vertical asymptote. There's a hole or a jump here. There's another jump here. So those 3 are all discontinuities. Automatically, we have a point of non-differentiability there. So x equals -6, x equals -2, and x equals 5. Okay, so we've got this vertical asymptote here, we've got this hole here, and this jump here. Those are all points that are non-differentiable because they have a discontinuity. We don't need to classify what kind of discontinuity, just the fact that they are is reason enough. Okay, let's look back at our our reasons why a function fails to be differentiable. So the first one was a discontinuity. The second one was a vertical tangent line. So if you're going along this function, I mean, you can find the slope anywhere here. You can find the slope anywhere here. Right, we already identified that as a problem. Here we might have a cusp, that's not a vertical tangent line. But the function is straight up and down, like right here at 7. All right, so there is a case where we have a vertical tangent line. So that is a point where we are not differentiable. Vertical tangent line. No slope. Undefined slope for the vertical tangent line. Okay, then we do have a cusp. There's no sharp turns here, but we do have a cusp, right? That cusp is given or shown right there, right? That's a cusp. Okay, so the last point we have is x equals 2, and that's a cusp. All right, so each of these points that we identified, they don't have a value of the derivative there. There's no slope actually at the points, but what we can do is the next best thing, which would be to find what the slopes are approaching as the x values approach these points. So remember, like with holes and asymptotes, we can't plug in a function value. We can still find what the function values are approaching. We're going to do that, but just with slopes. So let's find the limits of the derivative at these different, as these x are approaching these different values. So I'm just going to erase this for a second, just kind of bring this up closer so we can have more space to see everything. And so the first one that we're doing is we're finding where the what the derivative is doing as x is approaching 0. So x is approaching 0. So that is, well, where is that? That is on the x-axis, or approaching 0, so that's here, right? So we're looking at the function. The function value is up here, but we want to know what are the slopes doing. Okay, so we don't actually have any axis values here, right? So we can't find any numerical values. Our answers here are going to be positive infinity, negative infinity, or 0. So let's just remind ourselves, with lines that are horizontal, these have slope of 0. With lines that go up from left to right, these have positive slope. And with lines that go down from left to right, these have negative slope. So as you approach 0 from both sides, just sketch in little snippets of the tangent line. So if we go towards x equals 0 from the right, on the curve, maybe we have a little tangent line like that. As we get closer, tangent line become horizontal. Go towards 0 on the left-hand side, our tangent lines are just becoming flat. So that value is just 0. And that's actually a differentiable place. We can actually sketch in a tangent line there. So there's really no problem with that one. Let's look at 5 from the left. This was a place where the function failed to be differentiable. At 5, we have this jump, a point of a discontinuity. So as we approach 5 from the left-hand side, that's what this minus sign means, remember? So we're approaching 5 from this direction on the curve. And we're asking ourselves, what is the slope doing of the tangent lines? Okay, notice all of these are derivative, 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 derivative. We're finding limits of the derivative. So in other words, the slope of the tangent line. So we're going along the function towards x equals 5 from the left. So sketching little pieces of the tangent lines. So we're pretty close. Maybe at 4 it'll look like that. Maybe at 4.5 it'll look like this. Maybe at 4.9 it'll look like that. They're kind of leveling off. They're becoming less steep. They're a little bit positive, then they're a little less positive, and then they're getting pretty close to 0. So again, I would call that limit there equal to 0. From the right-hand side, as you approach 5, so that's down here, 5 with a plus means from the right. So we're going towards 5 from this direction, along the function. Now we wouldn't, again, normally be looking for the y value, but we're looking for the slope now, not the y value. So sketch in some tangent line snippets. I mean, the way this is, they're kind of all sort of horizontal, right? So we would have a 0 there for what those tangent line slopes are doing as we approach 5 from the right. -6 from the left. This was a place, we have this vertical tangent line, right? Another point of discontinuity. -6 from the left. So we're going towards -6 this way. We're following down the function this way. Okay, so as we get close to -6, maybe -6.5. So I've got this point here, sketching a piece of the tangent line. Maybe it'll look like that. Okay, it's negative. All right, so as we get closer to -6, maybe like over here, it's also negative, but it got steeper. I don't think it showed up yet. It's also negative, but it got steeper. If we pick a point that's even closer to -6 and sketch in a tangent line there, it's still negative going down from left to right, but it's even steeper. It's more vertical. So they're like, maybe this one here is like -10. Here we've got like -100. Here we've got like -1,000 or something like that, right? They're becoming vertical, but they're becoming vertical from the negative direction, or with lines that have negative slope. Right, so this will be, the slopes there will be getting large but negative, so that'll be -infinity. Okay, from the right-hand side, I know this is tough to think about. It's really tough to think about. I think drawing in the little snippets of the tangent line really help though. Okay, from the right-hand side as we approach -6, remember we're going towards -6. So maybe we'll draw a tangent line snippet like over here. Okay. That goes down from left to right. That has negative slope. As we get closer to -6, it's really kind of hard to draw these in. we're still going down from left to right, it still has negative slope, but it's steeper as we get closer to -6. So it'll be a larger negative number, like larger in absolute value. Right? As we get closer to -6 even more, it'll become steeper and steeper and steeper. And so again, this is going to be negative infinity. Okay, down here we've got the limit of the derivative as x is approaching negative infinity. So that's as x approaches negative infinity, that's going along the function this way. So the function is leveling off, right, and becoming more and more horizontal, less and less steep. So the tangent lines there are also going to become less and less steep, right? The slope of this curve is becoming 0, right? Because the function itself is kind of leveling off. And so every tangent line will have a slope near 0 and be getting smaller and smaller. So the limit of the derivative as we go towards negative infinity will be 0 there. Again, you can see that I know -9 isn't close to negative infinity, but you can tell already it's getting pretty shallow. Okay, moving over here, we've got the limit as x approaches 2 from the left, and then 2 from the right. So this is another point where we had a discontinuity, right? Here we have a cusp. So let's start with from the left first. So we're going towards 2 this way. So we're going towards the function this way. Okay, so I can already tell that this curve, it has negative slope everywhere, right? It's going down from left to right. So if we draw in some snippets of the tangent line, they're getting steeper and steeper and steeper. Eventually, they're going to become not horizontal, vertical. They all are negative slope though. So they're getting steeper and they have negative slope. Okay, so they'll become like -10, -100, -1,000, -1,000,000, right? So those are approaching a slope of negative infinity. Okay, it's all really coming down to these 3 options. That's all it is. Okay, 2 from the right. Let's see. So 2 from the right, we're going towards 2 this way. So we're going to put in some tangent lines. So let's maybe start here. There's one. Now that line has positive slope. Now I know we're going towards 2, but remember we think of slope as going from left to right. So this little snippet of this line has positive slope because it goes up from left to right. Okay, as we get closer to 2, draw in another piece of a tangent line. Okay, so like right here, that also has positive slope. It goes up from left to right. It's just, it's steeper in comparison to the previous one, right? If we go even closer, and it's hard to see, I was kind of like that. It still has positive slope. It goes up from left to right, but it's almost vertical. Okay, so this is what it looks like when these slopes are going to approach positive infinity, because they're getting steeper and steeper and steeper, but they all will have positive slope. Okay, lastly, we are looking at x approaching positive infinity. So that's all the way out on the x-axis here. Okay, so following the function, it looks like the function is trying to level off and get flat. And so the slope would just be approaching 0. Okay, so anything that flattens off will have tangent lines that get flatter and flatter as well, and those all have a slope of 0. Okay, so I would recommend you do have a problem like this on your homework, on your written homework number 3. I'd recommend that you maybe redraw this graph and see if you can figure out what these are without the answers and without watching this video, and then check back in with yourself, because it just takes a lot of practice. Once you see it, you can't unsee it. So this is the end of section 2.1. Next time, I will share with you some secrets about calculating derivatives that will make everyone's lives easier. Until then.